All right, so I'm not sure if I'm going to regret this or not because it's going to take a little while, but students have been telling me they're having trouble with relative velocity when it comes to vectors, so I'm going to do every single question from the textbook I'm using. Cambridge, hello. All right, let's get started. So this is the first question in relative velocity. We're going to keep in mind this formula here. All right, so the velocity of A with respect to E is equal to the velocity of A with respect to B plus the velocity of B with respect to E. And as long as we keep this formula in mind, we can't go too far wrong. Okay, so what do we want to know? We want to know the velocity of max with respect to the Earth. Okay, the velocity of max with respect to the Earth is equal to... Now, what do we know? We know that the river is flowing at 4 kilometers an hour. So the river is the intermediary bit. It's not max, it's not the Earth, it's the other thing. Okay, so that's going to be equal to the velocity of max with respect to the river plus the velocity of the river with respect to the Earth. And now I'm going to do something a bit non-standard here. I'm going to use this formula, but I'm not going to use this formula with numbers because this is a vector, this is a vector, this is a vector. I'm not even going to use it with like i's and j's. I'm going to use it with the actual arrows. So it says here, a river is flowing south at 4 kilometers an hour. Okay, that's the river. 4 kilometers per hour. River. Whee! Okay, that's a river. Max can swim at 3 kilometers an hour, and he dives in from the west bank and he tries to swim across the river. So he dives in from here and he starts swimming across, and he can travel at 3 kilometers per hour in still water. He can travel at 3 kilometers per hour with respect to the river. All right, taking this and putting it into our formula, the velocity of max with respect to the river is equal to 3, just like that. The velocity of the river with respect to Earth is equal to that, 4. So that means that when we add these two vectors together graphically, we can say 3 plus 4 makes 5. 4 makes 5. Why am I saying 5? Pythagoras. Okay, so in which direction does he travel? We need to find this angle right here. So SOHCAHTOA, tan theta is equal to opposite over adjacent, 4 over 3, and we put this into our calculator. So when I do that, I get an answer of theta is equal to 53.13 degrees, but this is a real-world application. It's not some sort of mathematical construct. This is 53.13 degrees, but we need to talk in terms of true bearings. So we start by facing north and we rotate around. So the answer to the question, in which direction does he travel? So the answer to this question is equal to 90 degrees plus the thing that I just found, 53.13, which is 143.13 degrees true bearing. You can do like some other bearing, but that's what we're going to do. What is his actual speed? Super simple. There's a reason they chose 3 and 4 here. His speed is equal to the square root of 3 squared plus 4 squared, which is root 25, which is 5 meters per, is it meters? Kilometers per hour. Okay, so that is question 1. Okay, moving on to question 2. All right, a train is moving due north at 100 kilometers an hour. So there's my train, 100 kilometers per hour. A passenger walks straight across a carriage from the east to the west side at 4 kilometers an hour. What is the true velocity of the passenger? Okay, so important to talk about this word here, velocity. So velocity is the magnitude, like their speed, but it's also their direction. When you use the word velocity, you're talking about direction and speed. So we need those two things. Okay, now the train is moving them along at 100 kilometers an hour. They're walking along at 4 kilometers an hour. So I'm not going to write up that formula again because I want you to understand that this is just going to be the addition of those two vectors. The train's pushing us along at 100 kilometers an hour. We're walking across at 4 kilometers an hour. So 100 that way, 4 that way. If we can find everything out about that vector, then we're in business. So I'll approach this one just a little bit differently, just for fun. Let's call this vector u. Vector u is equal to this first vector here, which is 100j, plus this vector here, which is this direction. So that means it's negative 4i. So that's vector u. Now we just need to know the magnitude of vector u, and we need to know the direction of vector u as well. So finding magnitudes of vectors, we should know how to do that. It's negative 4 squared, but that's still going to be just the same as 4 squared. And then 100 squared. All right, putting that into a calculator. So putting that into my calculator gives me 4 root 626. That number's pretty useless because this is an application. So let's change it to decimal. Okay, so our speed is 100.08 kilometers per hour. So that's the speed we were moving in, like that direction, right? What about the direction of this thing? So we should know how to find the direction of these things. It's tan theta equals, so what angle am I trying to find? What angle am I trying to find? I'm trying to find this thing here, right? So I can do tan theta equals opposite over adjacent. So negative 4 over 100. I can solve that. So the answer my calculator gives me when I do shift 10 of that is negative 2.29 degrees. Now that requires some interpretation, right? So we've drawn a picture of this. This 2.29, if I'd put positive 4, it would have given me positive 2.29. And so if I'm just doing it as like regular trigonometry and I draw the picture and I try to find that angle, I'll get 2.29 degrees. But this is the real world, so I don't want 2.29, I want the true bearing. So I start, let's get rid of that calculator. So I start from north and I rotate all the way around. Or I do 360 minus 2.29. Now, that gives me 357.71 degrees true. My final answer would be to write something like a speed of this with a direction of this. Now, some of you might be thinking, I don't want to think, like thinking's overrated. What you can do instead here, let's get rid of our calculator again, is to learn how to transfer negative 4i plus 100j from component form into polar form, particularly how to find that angle. So if you wanted to find this angle here, what you're actually doing is a little bit different. You're doing tan theta equals, and instead of doing negative 4 over 100, you're doing 100 over negative 4. Now, when you've come up with that answer, what's that when we put that into our calculator? Now, unfortunately, when we do that, we get an answer of negative 87.70. So what's an angle of negative 87.70? That's like down here. All right, so that does not feel helpful at all because you've still got to consider like a unit circle. You know, you might have learned like CAST. Tan is negative in this quadrant and this quadrant, and given the information we've got, that's the quadrant we wanted. So we're still going to have to use our brain and convert this angle, add like 180 to it and convert it to that angle over there. So no matter how you slice it, if you're not drawing pictures in these things, you're probably not going to get the right answer. On to question 3. All right, here we go. Cars A and B are driving along a straight level road that runs from east to west. I don't know what this question is. I just draw pictures as I go. If car A has a velocity of 100 kilometers an hour west. Okay, so car A is traveling 100 kilometers per hour in that direction. All right, so that's car A with a velocity of 100 kilometers per hour. Car B has a velocity of 80 kilometers per hour, also west. Also west. What is the velocity of car A relative to car B? Okay, so that's what we're answering, just part A. It's probably worthwhile looking at our formula again. Okay, velocity A relative to the Earth equals velocity of A relative to B plus the velocity of B relative to the Earth. And we're being asked, what is the velocity of car A relative to B? So we're trying to find this. Formulas work in all sorts of ways. If you want to find one thing and you know the other two things, you're fine. The velocity of A relative to the Earth is 100 in that direction. The velocity of B relative to the Earth is 80 in that direction. And this is the thing we want to find out. Now, we can manipulate these vectors the same ways that we would manipulate numbers. So, if I want to get my question mark by itself, I just need to subtract a vector of 80 from both sides. So, 100 minus 80 equals question mark. Okay, now drawing that, what does that look like? It looks like a vector of 100 minus a vector of 80 in the same direction, but because we're subtracting it, our resultant vector is going to be from the start of the first one to the end of the second one. Boop, boop. My answer is 100 minus 80 equals 20 in that direction. 20 degrees, 20 kilometers per hour in what direction? West. You can see in the question, that's how they're describing their velocities. They're saying this is 100 kilometers per hour west. This is 80 kilometers per hour west. So I'm describing my answer in the same way, 20 kilometers per hour to the west. You might be tempted to answer it with like negative 20i kilometers per hour. But that is meaningless in this context. We're talking about speeds and like compass directions, so that's what we should stick with in our answer. Part B. So in part B, they stick with 100 kilometers per hour to the west for car A, but they switch the direction of car B to 80 kilometers per hour east. All right, so then they ask the same question, what is the velocity of car A relative to car B? So we can do the same thing that we did before. 100 kilometers per hour to the west equals this question mark plus 80 kilometers per hour in that direction. So 80 there, 100 there. We rearrange just like we did before. So this time we get this 100 minus this 80. And that's going to be equal to my question mark. 100 minus a vector of 80 in the other direction. Now if you're subtracting a vector, it's adding the vector and flipping it. So we're going to get 100 plus, flip the vector, 80. And if we do that graphically, we get 100 plus 80 is equal to 180. 100 plus 80, 180. So my answer is 180 kilometers per hour to the west. All right, there is my answer to this question. Now again, you can like put I's and J's in here if you want to, but in the end, we're going to end up with 100 kilometers per hour to the west. Question 4 is, a cricketer is on a moving walkway which runs from south to north at 2 meters per second. I won't put the units in there. He bowls his fastest delivery, which is 45 meters per second, again in a direction north. So he bowls really fast. 45. What is the velocity of the ball relative to Earth? Okay, so we want the velocity of the ball relative to Earth. Now, that's a little bit confusing because I got my B here, but we just need to be a little bit clever about what we're doing. That's going to be equal to the velocity of B relative to A plus the velocity of A relative to Earth. Okay, so the velocity of B, that's the ball, relative to the walkway, right? Because he bowls his ball at 45 meters per second, but the walkway is moving along as well. So that 45 meters per second in that direction is how fast the ball's travelling. But we've got the addition of that walkway. That walkway is also going to add some to it. The walkway with respect to Earth. So the A is like the walkway. When we add two vectors like that together, 45 plus 2, we get 45 plus 2, and we get a total answer of 47. 47 meters per second. People are going to look at this answer and believe that they're going to be able to do something always that they can't always do, right? They're going to look at this and say, all right, I see two velocities, 2 and 45. I'm going to add them together and always get my correct answer. This is only working because the vectors are moving in the same direction. If the walkway was moving him like left to right and he was bowling like this way, you'd have to do something different. If like he was walking at a 45-degree angle and bowling different, you've got to add vectors a bit more like that kind of thing. So this question is a cautionary tale. If you do this question and no other one, and you just go 2 plus 45 plus 47, you get the right answer, you might get excited and think you're doing something clever, when actually, wrong thinking, correct answer. So, something to watch out for. Now, I did just rub it off the screen, but I did write that my answer was 47 meters per second. I'm wrong, because it says, what is the velocity? And remember, velocities have speed, but they also have direction. So, I'm wrong. I really need to add in my direction here. 47 meters per second in a northerly direction. Okay, on to the next question. A ship is moving in a straight line at 15 meters per second. A bird flies horizontally from the front of the ship towards the back of the ship at a speed of 5 meters per second relative to the ship. Okay, people get really confused about this question. So let's look at it. It is a boat. That is my boat. Okay, and my boat is traveling in this direction at a speed of 15 meters per second. Now, a bird flies horizontally from the front of the ship to the back of the ship. So moving in this direction towards the back of the ship at a speed of 5 meters per second. Relative to the ship. Okay, so that's an important thing to note, right? If someone was not on the ship and watching this bird fly, the speed that they'd be thinking in their head would not be 5 meters per second. Because they're not relative to the ship, they're relative to the Earth. This speed here is the bird relative to the ship. There's a person on the ship watching the bird. The person on the ship is moving with this arrow. So when they watch the bird looks like it's moving at 5 meters per second. Okay, so what do we want to know? What is the speed of the bird relative to the sea? The speed of the bird relative to the sea, so I'm going to try to use the right letters here, is equal to the velocity. All right, so that A is equal to the bird relative to, oh, that's bad, sea, ship, plus the velocity of the ship relative to the sea. Okay, so that's our sort of setup. We've got no Earth here. The sea is the Earth. Okay, so what do we know? We know the bird. This is a bit confusing. Bird, boat. Okay, so a bird flies horizontally from the front of the ship towards the back. The ship is moving in a straight line. So the ship is moving at 15 meters per second in a straight line. I've chosen that arrow. Someone might have chosen that arrow. Someone might have chosen that arrow. That arrow. I'm choosing that one. It doesn't matter, because all we know really is that the bird and the boat are moving in opposites. Now, the bird relative to the ship is this, 5. All right, and we're adding those together to get the bird relative to the sea. So that is just going to be 5 minus 15 minus 5, which is 10. If you want that graphically, 15 plus 5 makes 10. 15 plus 5 in the other direction makes 10. So there's my 10. It's meters per second. What is the speed? So it says speed of the bird, so we don't care about its direction, so I don't have to say north, south, east, west, which is good because the question didn't mention anything about north, south, east, west, so I'd be sunk. Sunk, boat. Awesome. Next question. All right, here we go. Question 6. Car A is travelling north, 60. Car B is on the same road, travelling north. So this is car A. Car B, also travelling north, but this time at 40. All right, so we want the velocity of car A relative to car B. So, what are we doing here? Well, we know A relative to the Earth, relative to the road, and we know B relative to the Earth. What we want to know is A relative to B. So, we can put this into our formula. We know that A relative to the Earth is equal to this, 60. We don't know A relative to B. That's the thing we want to know. I keep putting question marks in these. Maybe I should use vector notation here. So the vector u plus the velocity of B relative to the Earth, which is 40. So if I want to know vector u, I can rearrange this equation. 60 minus 40. Now, in terms of vectors, that's equal to 60 plus 40. And if I drew that picture, I'd get 60 plus 40 makes 20. So, vector u is equal to 20. How fast are we traveling? We're traveling kilometers per hour. And we want the velocity, so we need a direction. 20 kilometers per hour in a northerly direction, because our arrow is facing up. What about the next one? So, I'm going to do this the long way. Based on what we found out from part A, there's a really fast way to do this, but I'm going to do it the long way. Alright, so if we want to know the velocity of B relative to A, we need to rewrite this formula so that we can do something like that. So, velocity of B relative to A. So, everywhere I see A, I'm going to replace it with B. So, velocity of B relative to the Earth. And everywhere that I see B, I'm going to replace it with A. Okay. So, because I'm trying to find B with relative to A. So, I need that piece there. So that's the thing I'm trying to find. Velocity of B relative to the Earth is 40 in that direction. Velocity of A relative to the Earth is 60 in that direction. And then we can rearrange this like we would any other equation. 40 minus 60 with an arrow equals u. If we're subtracting vectors, we're adding the reverse of that vector. Okay. 40 plus 60 down, so we have 40, right there, 40 plus 60 down. That gives us a resultant vector of this one here, which is 20 kilometers per hour. So vector u equals 20 kilometers per hour south. Okay, now this feels strange. So let me talk you through it, because you've been in a car before. So this is a question that's a really good one to talk about. A is traveling faster than B, right? So if you were in car B, if you both were at the same spot at a certain time, if you were in car B, A would be moving away from you. So the velocity of car A relative to you in car B would be the difference between your speeds, right? A would be moving away from you at a rate of 20 kilometers per hour. Okay, that one feels okay. This next one gets a bit of a head scratcher, but again, you've seen it in action, so you're fine. The velocity of car B relative to car A. So, now you're in car A, right? And you and car B are right next to each other. Car A is traveling faster than car B. So, your car is going to go past car B and get away from it, right? But, if you look at car B, car B looks like it's going backwards, right? You're getting away from car B, but from your perspective in the car B is going backwards away from you at a rate of 20 kilometers per hour south. If you've ever been in like a train and it feels for a moment like instead of the train moving, the platform is moving, that's what's going on here. The platform relative to you is moving backwards. You relative to the platform is moving forwards. Okay, that's that question. Question 7. Okay, a plane is heading due north. Its airspeed is 240 kilometers per hour. There is an 80 kilometer per hour wind blowing from the west to the east. So, 80 kilometers. Okay, what is the velocity of the plane relative to Earth? So it's probably at this point that I need to talk to you a little bit about aviation. Airspeed. Airspeed means speed in the air, right? It doesn't mean that if you were on the ground watching this plane, that this plane would be traveling at 240 kilometers per hour north. What's actually happening here is the pilot, here's my plane, this is my plane, okay, and it's traveling in that direction. That's my plane. The pilot is pointing the nose of the plane north, right? But that wind, here's my plane, that wind is pushing the plane like this. So the plane actually looks from the ground like this. All right? Even though the pilot is facing the plane directly north, the plane is not traveling north. The plane is traveling the sum of its airspeed, which is the plane's speed with respect to the air, plus the speed of the air with respect to Earth. So the plane is traveling 240 kilometers per hour with respect to the air, and the air is traveling at 80 kilometers per hour with respect to the Earth. And if we add those two together, we'll get the velocity of the plane relative to Earth. So adding two vectors together, very, very simple, 240 plus 80, we get this as our solution. And it says, what is the velocity of the plane relative to the Earth? So we need two things for that. We need the magnitude of that, and we need this angle right here. You should really pause the video and try this, because you can find that magnitude and you should be able to find that angle. Don't be surprised if you get that angle wrong. If you do, you've just missed a little bit of a trick. So my answers here, the speed is equal to the square root of this squared plus this squared, which is 252.98 kilometers per hour. And that angle there is equal to opposite over adjacent, which is 18.43 degrees true. I said you might have trouble with this. You're not going to have trouble with this because that angle is the exact answer. We don't have to alter that angle to deal with true bearings or anything. There is north, and that angle, let's get rid of that calculator. There is north, and that angle there is the true bearing, which is 18.43. This question's one of the simpler ones, as long as you understand this idea of an airspeed. On to the next one. Alright, car A is moving at a velocity of 60 kilometers north. Car B is moving with a velocity of 80 kilometers west. That's straight across, sorry about that. Alright, all these are speeds. What is the velocity of car A relative to car B? So, this is similar to a couple of questions ago, but in the previous example, both cars were moving along a road together like this. This time, one car's moving like this, one car's moving like this. So, this could be tricky. But, as long as we consider our formula, we should be okay. So, we want to know the velocity of car A relative to car B. We know the velocity of car, this is car A, this is car B. We know the velocity of car A relative to the Earth, that's 60 straight up. We don't know this, let's call it vector U. The velocity of B relative to the Earth is 80 in that direction. So, rearranging this, we get vector U is equal to this vector here minus that vector, which is equal to that vector plus that vector. vector u. And then we can just add those vectors together. So that's going to be equal to 60 plus 80. This is the vector we're looking for. So 60, 80. Now, it says, what is the velocity? So again, we're going to need the magnitude of this. We're also going to need the direction of that. You should really try that, because I think you can do it. All right, the answer is going to pop up in a few seconds. So we get an answer here of a speed of 100 kilometers per hour and a direction of 53.13 degrees true bearing, right? Now, it's really worth trying to visualize this in your head. What is the velocity of car A relative to car B? So imagine you were in car B, and imagine that you were traveling at 60 kilometers per hour. 80 kilometers an hour west. All right, so you're in car B, you're traveling west. You see a car over there somewhere, you look left, and you see a car, and it's traveling at 60 kilometers in a direction of north. Relative to you, imagining that you're standing still, the car is traveling faster than it actually is. It looks like it's traveling faster than it actually is. It's traveling 100 kilometers an hour from your point of view, and it's not traveling north from your point of view. From your point of view, it's traveling away from you because you're moving away from it. It's a real head scratcher, but that's relative velocity. Question 9. A glider P is traveling north at 60 kilometers per hour. Another glider Q is traveling northwest. Whoops. Never eat soggy Wheat Bix. Okay, it's traveling northwest at 40. Find the velocity of P relative to Q. All right, so again, we're trying to find the velocity of the two objects, P relative to Q, given we know the velocity of P relative to the Earth and the velocity of B relative to the Earth. So P, that was our first one here, is 60 straight up. P with respect to Q, we don't know. And the velocity of B with respect to the Earth is 40 that way. I think this is the first time we've had like a diagonal one. Okay, rearranging this, 60 minus a vector that looks a bit more like that. We have vector u here. If we subtract a vector, it's the same as adding a vector in the other direction. And now let's get rid of that. And let's draw a picture of what this looks like. 60 plus 40 makes this vector here. Okay, what do I know? I know that this was northwest, right? So I know that this is a 45-degree angle. So I have a 60, I have a 40, I have a 45-degree angle. I'm trying to find the velocity, which means I'm trying to find the speed, the magnitude of vector u, and I'm also trying to find this angle here. So this looks like a job for the cosine rule, because this is the first question we've run into that doesn't have a right angle in it. So, cosine rule, try it out. So that's my first line of my cosine rule. The magnitude of this side squared is equal to this squared plus this squared minus 2 times this, cos 45. Put it in your calculator. So when I put that into my calculator, you can see my answer there, 1,805. But of course, I need to square root that answer. So u, the magnitude of u itself, is equal to the square root of all of that, which is 42.495. Let's just make it 42.50. What are my units? We're talking kilometers per hour. Now that I have the magnitude of that, I can use the sine rule to find that angle there, right? So I could say that sine theta over 40 equals, and let's use this angle here, 45, and this length here. So sine 45 over this one here, which is 42.5. So then rearrange that and solve for theta. Now, when I solve that, and you can see my calculator there, I get an answer of 41.72 degrees. Now, the textbook doesn't have that answer. The textbook has a different answer, like 221 or something. Now, of course, it's possible that I've made some sort of mistake here, so let's look again. Glider is traveling north, yep. Another glider is traveling northwest. Now, I did write northwest here, and then I had to reverse it, so it came back down here. And so I'm pretty confident that vector plus that vector is that angle right there. An angle of 221 is like this thing right. It's like there. All right, so it's possible that I have made some kind of error. So let's put ourselves in the mind of the velocity of P relative to Q. Okay, so imagine that you were in a glider traveling northwest. Okay, so the glider's going this way, right? And it's traveling at 40 kilometers per hour. There was another glider, P, and it's traveling north faster than you are. You're traveling 40 kilometers an hour, and they're traveling 60 kilometers an hour. So if we continue on like this, it definitely feels like, if you're in here, it feels like this thing is going to eventually pass you by, right? You're traveling 40 kilometers an hour, they're traveling straight up at 60 kilometers an hour. I think they're going to go away faster than you, right? Which means that in your mind, it looks like they're going to be moving in that direction. They're going to be moving upwards and like away from you. So kind of like that. Hard to get your head around, but I'm feeling pretty confident. 41.72. I don't think this glider is going to look like it's traveling at a true bearing of 221 degrees. You're moving this way, you're moving that way. This glider is not going to look to your eyes like it's moving down here. It's going to look to your eyes like it's moving away from you and upwards, I believe. Textbook's wrong. I'm feeling good about this answer. Come at me if you can prove that I am in fact wrong. Next question. What is it? Two particles, A and B, are moving with constant velocities of 4i minus 3j, and VB is moving at 5i minus 7j. Find the velocity of B relative to A. All right, so what am I trying to find? I'm trying to find one of those things again where we're finding the things relative to each other. So we're doing the velocity of B relative to A, which means that we want the velocity of B relative to the Earth plus the velocity of A relative to the Earth. That's the thing. We want to know this vector here. What do we know? We know that the velocity of B relative to the Earth is 5i minus 7j. Let's get fancy here and write it like this. 5 minus 7. VA, the velocity of A, is 4i minus 3j. 4 minus 3. Okay. So again, this feels easier. I could draw all this. Let's go pure algebraic, right? Minus this vector right here. All right, so 5 minus 4 is 1. Negative 7 minus 3. Negative 7 plus 3. Negative 4, I hope. Okay. Find the velocity of B relative to A. The velocity of B relative to A, believe it or not, my answer is 1. So I minus 4j. I don't need that bracket because I've swapped back over to I and j components. I minus 4j meters per second. So you might be looking at this going, okay, so it asked us to find a velocity. So we need magnitude and speed. This encompasses magnitude and direction. This encompasses magnitude and direction. We're told that we're moving one component across and 4 components up every second. 1 meter across and 4 meters up, 4 meters down, sorry. 1 meter up across, 4 meters down every second. 1 second, 2 seconds, down, 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 down. 1 second. Okay, that's the velocity of B relative to A. Part B, super straightforward, not worth thinking about. Find the magnitude of this relative velocity. It's root 17 meters per second, which is 4.12 meters per second. So this is the answer to part A. Velocity can be spoken about in I and J components in this instance because this does tell us magnitude and direction in a single shot. If you want to just find the magnitude, here's what's happening here. It definitely feels like part B is easier than part A. I think the textbook authors were hoping to show you that difference between velocity and magnitude of velocity. Part B is not supposed to be harder. Part B is just supposed to be illustrative of the differences between these two things. Next bit. Here we go. Your battery is running low. Uh-oh. All right, I'll be back. All right, plugged in, ready to go. Next question, what do we got? A ship is moving in a straight line at 15 meters per second. A bird flies at an angle of 18 degrees to the horizontal from the front of the ship towards the back of the ship. All right, so we have a boat. This is a picture of my boat. It is traveling in a straight line at 15 meters per second. A bird flies at an angle of 18 degrees to the horizontal. So this is the horizontal. From the front, this is the front of the ship, to the back of the ship. So the bird is like perched on the front of the ship and it takes off. But in the process of taking it off, it flies at an angle of 18 degrees at a speed. And so the magnitude of this is 5 meters per second relative to the ship. And we want to know what is the speed of the bird relative to the sea. Okay. Velocity of the bird, B for bird, relative to the sea. Let's go O for ocean. The velocity of the bird relative to S for the ship, plus the velocity of the ship relative to O for ocean. Okay, so the velocity of the bird relative to the ocean, B for bird, the velocity of the bird relative to the ocean is unknown. We don't know this. Oops. Okay, so vector U, we don't know it. We don't know the bird relative to the ocean. We do know the bird relative to the ship. Magnitude of 5 and an angle here of 18 degrees. And we do know the ship relative to the ocean, 15. Okay, so if we add those two vectors together, we'll have our answer. Now, you could have drawn this picture differently. You could have drawn the boat moving straight up and the bird like this. You could have moved the boat going this way and the bird like this. So we don't have to talk in terms of I and J components here because different people's questions would have different I and J components because their boat went this way or this way or this way or this way, and the bird obviously had to follow suit, right? So we can think about this purely graphically. We can say 15 plus this vector here, 5, let's make it shorter because it's only 5, and an angle of 18 there. The result of adding those two vectors is going to be this answer right there. Alright, so this is some sort of triangle question. I see two sides and an included angle. So cosine rule. They're asking for the speed of the bird, which means I don't need the direction. I only need the magnitude of that purple vector. So doing that, we get an answer of 10.36 units. What are we? Meters per second. Okay, so again, these relative velocities, something relative to something else, not relative to the Earth, really hard to get your head around. If you're on the boat and you're traveling at 15 meters per second and it looks to you like the bird is traveling 5 meters per second that way, then roughly speaking, the bird is traveling 10 meters per second relative to the sea, right? Because you're traveling at 15, the bird's traveling at 5, roughly the bird's traveling 10 in that direction in actual fact. The 0.36 comes from the fact that the bird is not traveling, like it's not like 15 and 5 to make 10. It's 15 and 5, and you get that slight variation in that speed because of that angle. Great question. I'm getting a little bit tight here, but I'm going to keep pushing through. Next question. A light aircraft has an airspeed of 240 kilometers per hour. The pilot sets a course due north. The wind is blowing from the northeast. The wind is blowing from the northeast. So northeast is over there, so the wind is blowing like that at a speed of 70. Okay, what is the true speed and direction of the aircraft? Okay, so the plane with respect to the air, is 240. The air with respect to the earth is 70. And we're going to add those together to get the plane with respect to the earth. So we're going to get a vector plus another vector is equal to, different color, that vector. And that's the vector we're trying to find. 240, 70, and this angle here, because it's blowing from the northeast, this angle here is 45 degrees. 45, that's a 70, 70, 240. That's another job for the cosine rule. Okay, getting a little bit annoyed with the cosine rule, but let's do it. So there is my cosine rule, and my answer is 196.83 kilometers per hour. So that's the magnitude of it, but I don't know the direction. So I need to use like a sine rule to find the direction here. So now that I know that that's 196.83, and I want to find this angle right here, I can do sine theta over 70, the opposite side, is equal to, we use this number here, sine 45 over 196.83. Okay, rearrange this for theta, so we get inverse sine of 70 sine 45 over 196.83. And calculator. Now that gives me an answer of 14.56. Let's go with 14.565 degrees. But that's not the answer, because we're trying to find what is the true speed and direction. This is that angle in this triangle, but we're looking for a true bearing, right? So if that's north and that angle is 14.565, the direction of our object is equal to 360 degrees minus 14.565 degrees. Calculator. So we get an answer of 345.44 degrees. A little bit of rounding. That's it. Again, if we've got our formula, if we know how to add vectors graphically, nothing's too tricky. All right, we're getting close. Question 13. An aeroplane with an airspeed of 200 kilometers is flying to an airport southwest of its present position. There is a wind blowing at 70 kilometers an hour from the east. Find the course that the pilot must set. Oh, okay, this is a good one, right? Because what do we know? We know that the aeroplane has an airspeed of 200 kilometers an hour. So airspeed is the plane's speed relative to the wind, right? So that belongs here, plane relative to the wind. All right, and that speed is 200 kilometers per hour. Now, an airplane with an airspeed is flying to an airport southwest of its present position. Okay, so if a plane wants to go southwest, it wants to travel in that direction, that is a direction relative to the Earth. Okay? The plane relative to the Earth. And we want to go southwest. We want to go in this direction. Okay. There is a wind blowing 70 kilometers an hour from the east. So that's the wind relative to the Earth. 70 kilometers from the east. Never eat soggy Weet-Bix. There's east. That way, 70. All right, this is the first time we've seen a question that looks like this, because we've actually got elements from everything here, right? We've got a magnitude of this vector, we've got a direction of this vector, and we have this vector here. So, how do we do this? Okay, we know that a vector plus a vector makes a vector, right? So let's draw a nice big picture of what we're dealing with. We want the plane to do this, right? We know that there is a wind blowing in this direction. And so if the wind is blowing in that direction, and the wind plus the plane will be the result, the wind plus the plane will be the result, this is the plane. Okay, so drawing this all together now, the wind directly across at 70. The plane, we don't know the direction of it, but we know it's 200 kilometers per hour. And this part here, we don't know the distance. We don't know the speed. There is no speed between one place and another, but we do know the direction, 45. Okay. So, what does it say? Find the course that the pilot must set. So, the course that the pilot must set has something to do with this angle here, right? Because the plane's going to be pointed like that, and the wind's going to blow it this way, and it's going to end up here at the end. Plane pointed like this, wind pushing it, and so this angle here is what we need to find. How can we find that angle there? It feels like a job for like the sine rule, the cosine rule, something like that. Okay, I know what I'll do. I've got this angle here, I've got this side here, I've got this side here. With that side, I'm going to find that angle first. I'll just call it beta. If I find beta, I know the internal angles of a triangle, which means that I'll know the thing that I actually want to know. So, sine beta over 70 equals sine 45 over 200, and rearrange that to find beta. So that gives me a beta of 14.32. Now that angle is not fully useful yet because that's beta, but I don't want beta, I want this one here. Let's call that theta. So theta is equal to 180 minus 45 minus 14.32, which is some kind of number minus the answer, which is 120.67. That feels good because that's like, that feels right. That's still not my answer though, because it says find the course that the pilot must set. That angle there is 120.67, but the course that the pilot must set is a true bearing. Start at north, rotate through 90, then add the 120. So the course we need is equal to 90 plus that, which is 210.67 degrees. So 90, the first 90, plus that bit there, which is 120.67. So that is my answer to part A. What about part B? Find the speed of the airplane relative to the ground. Okay, that feels relatively straightforward, right? Because I know all the angles in that triangle now. The only thing I don't know is one of the sides. So it's just a repeated sine rule question. Okay, so sine... Okay, I know beta is 14.32, so I'll use that. So sine 14.32 over whatever's opposite beta, which is 70, equals, I can use that 200 and that 45 again. So sine 45 over 200. All right, so just rearrange and solve. Oops, can you tell I'm getting tired here? Okay, that doesn't work. What am I doing? I'm trying to find this. This is the thing I'm trying to find, right? So let's put it into our equation. That would be helpful. The opposite angle, again, got to be careful here, right? That angle is not 210. That angle's this. So 120.67. All right, not going to use a question mark because I'm not a child. X, and now I'm going to solve it. All right, I've rearranged it. Calculator, 243.27. What am I finding? I'm finding the speed, kilometers per hour. Now, it's worth stopping for a moment and making sure that that makes sense. A wind of 70, an airspeed of 200. Our speed with the wind combining with that should be more than 200. 243. Okay, I like that. One more question. All right, what's it going to be? A canoeist can paddle at 2 meters per second in still water. He wishes to go straight across a river so that his path is at right angles to the bank. The river is flowing at 1.5 meters per second. Okay, so this is another question similar to the previous one where it feels like we know a little bit of everything. We know that he can travel 2 meters per second in still water. So his speed relative to the water, is 2 meters per second. All right. So speed is just 2. Okay. That's the magnitude. Let's call it like meters per second. He wishes to go straight across a river so that his path is at right angles to the bank of the river. It's going to be easier for me if I draw a river. This is my river. And my river is flowing in that direction. Okay. So he wants to go straight across the river, right? So his velocity with respect to the Earth, he wants it to look like that. Don't know about the magnitude of it. The river is flowing in that direction at 1.5. Okay, so really the tricky part here is the setup. So, but I have a feeling this is going to be a little bit nicer because we might have a right angle triangle somewhere. Okay, the resultant, the end goal here is for him to look like this, and that is going to be equal to the river plus his movement, his canoeing, right? So this is the river, and the river has speed of 1.5. His goal is to go directly across the river, not like that, not like that, not like that, not like that, but straight across. And he is capable of traveling at a speed of 2 meters per second. Okay, so it says find the direction in which he must paddle. So we need to find that theta there. Thankfully, there's a little right angle there. So that feels like it's going to be super easy. Opposite over hypotenuse, so sine theta equals 1.5 over 2. Theta is some number. So a calculator says 48.59 degrees. Okay, so this is a little bit weird because they didn't tell us which direction the river was going in. I chose this direction for the river. The river could have been going this way, any direction. So it says find the direction in which you must paddle. You got to write 48.59 degree angle to the bank. Against the current. Something like that. Okay, what's the next bit? If the river is 60 meters wide, how long will it take him to cross the river? All right, so we know this angle here is 48.59, right? I've gotten rid of all my working here so we can draw a big picture of our river, because now we know that our river is 60 meters across, right? And we need to get from there to there. Now, The paddler is going to paddle that way at 2 meters per second, but that's not where they're going to go. The path of the paddler, because of this, is going to be along this line here. So we really want to know what is the speed of the paddler along there. And we can find that easily enough using Pythagoras' theorem, right? 2 squared is going to be equal to this bit here, c squared plus this bit, 1.5 squared. 4 minus 2.25 is equal to c squared. 1.75 is equal to c squared. So c, which is the speed of this rower, is going to be 1.32 meters per second. Okay, let's just check this out a little bit. They've got to row against the current here, and the river's pushing them this way. It makes sense that they're going to be making slower progress across here. So 1.32 meters per second. They've got to travel a distance of 60 meters. So speed equals distance over time. We know the distance they have to travel, 60. We know the speed that they're going to be traveling at, 1.32. We're trying to find the time it will take. So 60 divided by 1, let's use the answer, shift answer equals. So the time that this person is going to take is 45.36 seconds. All right. That, thankfully, is the last question. I have no idea how long I've been going for, but it's a bit of a marathon. That is every question on relative velocity.